Hi pre-calc students, Mrs. Fellon here. This is the last video for this first unit, so congratulations on making it this far. We are actually covering, it's video 3, so unit 1, video 3. We're covering sections kind of 1.8 and 1.9. And again, hopefully you have your notes and you're following along with me. All right, so let's kind of get into it. So we're going to start by just kind of going over how to add, subtract, multiply, and divide functions. I'm not going to give an example of every single kind, but I'm going to do a couple so that way you can see them. All right, so I'll pick the two that kind of give people the most issues, and that's subtraction and division. So for the first one, what we're going to get at is we're going to look at this notation. So first I give you some functions. So here's f of x, here's g of x, here's h of x, here's j of x. And so this is just kind of giving you like a catalog of which types of functions we want to use. This particular example says f minus g of x. That notation might be new to you. And so how else I want you to think of this when you see that f minus g of x, it's asking you to take f of x, which is this function here, and subtract your g of x equation. That's all it's really asking you to do. So as long as you know that these two things are equivalent, that shouldn't be too challenging. So let's do that. Let's take our f of x equation, which in this case is x squared, and then we're going to subtract our g of x equation, which is this. So here's the issue that I find to be the biggest mistake, is that people will do this and be like, all right, I'm done. The problem here is that because we're subtracting the entire function, you need to put this in parentheses. So it's not just subtracting the 1 right here, you're subtracting the 1 minus x. So we're going to do a little simplifying. I'm going to distribute that negative. And then because I like things in the correct order, standard notation, if you will, I'm going to go ahead and write it from highest to lowest. So x squared plus x minus 1. All right, it wasn't too bad, right? So now let's do division. So you'll see h over j of x. Again, what I want you to remember is that literally means you're taking your h of x equation and you're dividing it by your j of x equation. So h of x is this one here. So it's the square root of x minus 3. And your j of x equation is the square root of 16 minus x. Okay? And so this is what your function looks like. This is kind of a weird looking function, but nonetheless, it's still what we're asked to do. If you could have simplified anything, or you can, since we can't, we're not allowed to kind of separate this minus 3 from the x or this minus x from the 16. We're kind of at a standstill. So the only other thing I might have you do with this is talk to me about the domain of this function. And we're going to get into this a little bit later as well. But I want you to understand kind of where is this function defined, okay? So domain means x's, if you remember that. And so when we look at a rational function, this is a fraction with a letter or a variable on the denominator of your fraction. When we have a rational function, you have to think about which values of x would work, because there are going to be some times where things don't work. For example, in a fraction, you can never have the denominator of a fraction equal 0. Because what this actually does equal is it equals something called undefined. In other words, it doesn't exist. So there's going to be a whole bunch of numbers here in this particular example. Anytime you have a fraction, there's going to be with a variable in the bottom, so like a rational expression. You're going to have some values that don't exist. So how you decide is you look at this denominator. So in this case, it's the square root of 16 minus x. And you want to know when this function is equal to 0. So if I square both sides, I get that, right? If I square this and square that, I'm just going to move the x over so I get x equals 16. When x equals 16, this becomes a 0 on the bottom of my fraction. I can't have a 0 on the bottom of my fraction. So this means my function doesn't exist when x is 16. Here's another aspect. It's a square root function. Actually, the numerator and denominator are square root functions, correct? So with a square root function, there's something else you have to take in consideration. With a square root function, it not only can't equal, actually the square root of, you can take the square root of 0, you just can't take the square root of a negative number. So I have to look at this and say, whenever x minus 3 is less than, like it doesn't exist when it's less than 0. So when x is less than 3, my function doesn't exist. And then if I look here, 16 minus x, when that is less than 0, my function also doesn't exist. So this, I'm just going to rewrite it the other way. So this says 16 is less than x, or in other words, x is greater than 16. So these are going to be all parts of my function is undefined. It's undefined when the fraction has a 0 on the bottom. That's when x is 16. It's undefined when x is less than 3. It's also undefined when x is greater than 16. Okay, so if these are all the places where it is undefined, where is it defined? Well, great question. It is defined, okay, so it's going to be defined when x has to be, it's undefined when x is greater than 16, and it's undefined when x is equal to 16, but it's defined, in other words, it exists when it's less than 16. So when x is less than 16, we're good. Also, my function is undefined when x is less than 3, which means it's defined when x is greater than 3. Actually greater than or equal to, right? Because it could equal 3. That's okay. It just can't be, it can't be greater than, or it can't be less than 3, I'm sorry. Because if it's less than 3, then this would be a negative number. Okay, so you will not see me write it like this. So although this is the place where my function is defined, I'm just going to write that word in here so you know, you're going to see me write it like this. We call this interval notation. We're going to be using this a lot this year, and so the quicker we understand what this means, the better off we're going to be. So when we write interval notation, we write it in an interval. That's why they call it interval notation. But basically what this means is this is the lowest value that exists, and this is the highest value that exists. So it goes from low to high. So the lowest value that exists is going to be 3, and the highest value that exists is everything up to 16, but not including 16. There's the difference between the parentheses and the brackets. The brackets means we include 3, because remember, it could be equal to it. And the parenthesis means we don't include, because we can't have it include 16, because remember, that would cause my fraction to be 0. So that's the difference between the parenthesis and the bracket, why I wrote them like that. And so what we're looking at here is this means the same thing. This means all values of x that are less than 16, but greater than or equal to 3. That's what that means in words. You've probably seen it written like this before, or maybe as an and inequality, like x is less than 16, but greater than or equal to 3, like that. But you're going to see us, in all of the pre-calc world and beyond, write it in something called interval notation, which looks like that. All right, let's do some more stuff. We're going to get into composition of functions. So composition of functions, we are going to go over some more in class, but I wanted to give you a heads up on this video just to see what you guys could do and how much you can actually kind of do on your own, and then we'll practice some more in class. So hopefully you've done this in Algebra 2. I'm not 100% sure, but I think you have. What this means is f, and this little dot means of, f of g of x. We'll also see it written like this. This is generally how I write it, f of g of x. It means the same thing. It means a composition of functions. And you might ask, okay, well, what does that mean? Well, good question again. What it means is that you're taking one function and putting it into the other one. So you're taking your g of x equation and you're plugging it into this other equation wherever you see x. That's what that means. You're starting with f of x, you're taking your g of x equation and replacing x with whatever that is. So it's going to look like this. So 2 times, so instead of x, I'm going to write 4x squared plus 1 plus 5. That's a composition of two functions. Now, what we want to do is we want to simplify that. So we would distribute. Remember, we're not solving anything here. We're just simplifying, right? So we're just combining like terms. This is what we call the composition of f of x and g of x. So a linear function composed with a quadratic function gives me a quadratic function. That's kind of like the marriage of two functions and what happens, what happens when they're done. All right, let's do the other way around, because you can do a composition both directions. So what this means is g of f of x. So same kind of deal. You'll see me kind of write it like this a lot of times. But this time we're taking the f of x equation, so we're going the other direction. We're taking this one and plugging it in here. So instead of saying 4x squared plus 1, we're going to say 4 and then 2x plus 5 squared plus 1. Be careful how you simplify this. Remember, this is a binomial squared, which means, yes, whoops, this is a 2. You have to square the binomial. In other words, multiply by itself. You can't just square each individual term. That would be wrong. So if I FOIL this out, that'd be 10x, this would be 10x. So if I'm going too fast for here, go ahead and pause me. But all I'm doing here is just multiplying this out. I'm going to distribute now the 4, so I get 16x squared plus 80x plus 100 plus 1. And the final step is just to combine any like terms. And since the only like terms I have are the 100 and the 1, I get 101. And that's it. That's a composition of functions. Okay, so again, we're going to hit this again in class. I just wanted to kind of give you a head start on this because I think it's somewhat of a challenging example or challenging concept if you have never learned it before. If you have, great. If you haven't, well, we'll hit it again in class. All right, now we're going to switch gears and talk about inverse functions. You may have talked about these too. I don't know. But inverse functions, we're going to talk about all the different aspects of an inverse function. So an inverse means kind of like the opposite of. When you think of an inverse, I want you to think of what is the opposite operations being done. So for example, think of your linear function, 2x minus 3. Here's x. When you find the inverse of this function, we're gonna find this informally. In other words, what that means is I'm not gonna do a bunch of fancy math. I'm gonna use my brain. Imagine that. And so what we're gonna do is we're gonna say, what's happening to x? Well, x is being subtracted by 3 and multiplied by 2. Subtract 3, multiply 2. Okay, great. What's the inverse of subtract 3? Well, it is add 3. What's the inverse or opposite of multiplying by 2? Dividing by 2. That's what it means by finding the inverse informally. It means you're looking at the function and you're thinking about the operations and thinking about undoing them, or in other words, doing the opposite. So again, I always kind of start with the subtraction or addition stuff first in this one. So I would do the opposite of subtraction, which was the addition, the opposite of multiplication, which was division. Notice that I wrote f in this little line here of x. This means f prime of x. And so just so that you understand the notation there, this is the notation for inverse. If you see that written in calculus, we use this a ton. We use that little dash there. It's called a prime. And so you'll see that a lot. That's just a different notation. It just means the inverse of x. Okay, that wasn't too bad. Now let's talk about verifying inverses. This is probably what you did do in Algebra 2. I know I taught it with my honors classes. I'm not sure if they taught it in regular Algebra 2 or not. But basically there's a rule. There's a theorem. Not like a, kind of like an old school geometry theorem, but this is a little bit easier. The theorem states if I have two functions like h of x and k of x, if I do the composition of the function one way and it equals x, and then do the composition of the function the other way and it equals x, then we know they are inverses. Like this and this are inverses of each other. This is a proof, this is a way to prove that two functions are inverses of each other. So we're proving that two functions are inverses of each other. So again, this is not the algebraic method. We're going to get into that in a minute. But the proof of like how we can know that two functions are inverses, you know, like why all this exists, is if the compositions, both directions, equal x, and I have to do both directions, then we know that they are inverses. So that's what we're going to do. We're going to take two functions, we're going to compose them both directions, and we're going to see if they equal x. So let's do h of k of x. So I'm going to take the k of x equation, I'm going to plug it into this equation for x. So I get 7 times x minus 4 over 7 plus 4. All right, remember geometry. Geometry is all about, if you remember, we did quite a few proofs in geometry. It was about your thinking. This is not about the, you know, can you simplify this in one step in your head? I know you can. You already know the answer to this question. It's x, right? I already told you. So what we're getting at here is I need to see your evidence. I need to see step by step. This is your composition. Great. Step 1, how can you show me that this equals x? Well, the first thing I would reduce are my 7s. So I get that. That's step, I guess, 2. This is step 1, this is step 2. Step 3, I would subtract or cancel out my 4s. I need to see this process. That's what this is about. It's not about the fact that it equals x. It's about the fact that you're showing me that it equals x. So I need to see all the little steps. And it's not like I'm asking you to do a whole bunch. I'm just asking you to do like 3 steps here. But I need to see all 3 steps. In addition, I need to see the other direction. In other words, I need to take this and plug it in here for x and show that it equals x as well. So we're going to take x minus 4. In other words, 7x plus 4 minus 4 over 7. That's the composition of k of h of x. Okay, step 1, I'll do one thing per line. What's the first thing that we can reduce? Well, hopefully you're saying the 4s. Great. Hopefully this is pretty easy. Now we see the 7s cancel. Oh, voila, they both equal x. Why is this happy? Because I just proved that these two functions are inverses. Now, there's an easier way to do this when they're linear, like pretty easy functions like this. But when the functions get really complicated, this proof comes in handy. Okay, that's all I'm saying. All right, last but not least here, we're talking about verifying functions algebraically. Nope, I didn't say that right. Graphically, we'll do algebraically in class. All right, so maybe one time, a long time ago, you might have learned, maybe not, I don't know, that when you are looking at an inverse function, what you're actually doing graphically is you're doing a reflection over the line y equals x. That's what an inverse is. It's a reflection. So again, kind of pulling back to our geometry roots. Remember we did reflections, rotations, transformations, all those kinds of fun things. So if I had, let's say I take a parent function. Let's take my, let's take my square root function, my basic square root function. And I start at 0 and my function goes like this, right? So that's my parent function for a square root function. If I translate that or reflect that over this line, in other words, I take all these points, I fold my paper along this line and I translate it, if you will, it's gonna look like this. So if you can show that two functions have a reflection over the line y equals x, then you know they are inverses of each other. Because inverses mean that there's a reflection across, graphically it means there's a reflection across this line. So let's call this function, we're going to call this one the square root of x. And we're going to call this function, what's the inverse of a square root? Maybe you know, is an x squared function. But this isn't just a parabola, because we only graphed one part of it. This is just the parabola when your function is greater than or equal to 0. So there's like a little, side note or caveat there that you had to kind of do in order to get this picture. But what I want you to understand is all of this stuff, if I were to graph these two functions that were inverses, they would have a reflection across a line y equals x. Like all of these are interconnected. And so we can look at inverses, we can think about them kind of in our heads and think about, okay, what's the opposite operation? We can prove that they're inverses using compositions, right? We can show or prove that they're inverses using graphs, like some geometry. And then when you're coming to class next, we're going to talk a lot about, and I'm going to go through how to do, how to find an inverse of a function's algebraically, because obviously there's a lot of algebra in pre-calc, and so that's kind of where we're going to focus. And so we're going to kind of tie all of this stuff that we just talked about together into algebraic understanding. All right, that's it. That's all I have. What I'd like you guys to do is, if you have any questions, make sure you record them, write them down or something, and then bring them to class so that I can answer them. And I will see you soon. Bye for now.